figure out how not to make an amphibious car, right? Combine the best of both hierarchical and island-style FPGAs. How would you combine them? What do you think, Isidore?
Two different things. I'd say first off, if you look at like you can group together in a lab, I can't remember what they call it in Thailand, but group together a bunch of logic elements where they have a lot of fast routing between them, and then if you want to go to a different one, you can go up the hierarchy to the general routing,
Yeah.
island style.
So you're saying use like hierarchical at the bottom of the hierarchy. So make a logic block like a CLB in Xilinx terminology, lab in Intel, and then connect it with island style. So that makes it, so that seems reasonable. What do you think?
You make the VLSI designers cry. You do a hierarchical, then you do a non-hierarchical, and then hierarchical, non-hierarchical, every single layer. So it's impossible to make, but it will route amazingly.
Wow, that's worse than an amphibious car. That's like sort of like that's like an amphibious helicopter or like some kind of amphibious car plane. So, but I believe you were shooting for that. So, yes, that would be hard. But yes, Isidore's got it exactly right. So you can hybridize these two types of architectures, and that's exactly the right way to do it. Okay, so remember we had done A and B, we're now doing C. C basic style of architecture is hybrid. And yeah, so again, the value of hierarchical was the CAD was simpler, but that was starting to break down as we had to start putting, we kind of really couldn't make the really long wires that a hierarchical FPGA would like for the top level. And it had kind of worse scalability. As they got really big with hierarchical, so maybe I'll write that down. So hierarchical had an advantage, which has been diminishing, but it did have an advantage of simpler CAD. I guess it still kind of has that. It's just CAD tools are getting better, so maybe it's less important nowadays. But it has the problem of it didn't scale as well. So it's kind of long wires. That was one big problem. We wound up with these really long wires that are actually not efficient to make anymore at the top levels of the hierarchy. And the other thing is what we call fixed bandwidth. Okay, at the top level of the hierarchy or upper levels of the hierarchy, you have these expensive wires. You'd rather not make very many of them, but that gives you only so much interconnect. And we saw that if your design needs more interconnect than that, it has a higher rent exponent, you had to space out the design a lot. So that was kind of painful. But these problems are not very significant if it's actually a small amount of logic that you're combining in a hierarchy. So yeah, we can use hierarchy or use hierarchical design techniques basically at the lowest level of hierarchy. Okay, and it's for exactly the reasons Isidore's flagged. Like the wires are still short. If we don't combine too many things in a hierarchical FPGAs, these problems of really long wires don't come into play. So what people usually do, so this is commonly employed in most commercial FPGAs, and the terminology differs from manufacturer to manufacturer. The academic terminology is usually you talk about basic logic elements. Okay, so that's like a LUT plus a flip-flop would be the most common thing. Might be a little more complicated than that, but it's like a little bit of logic, usually formed out of a LUT and one or two flip-flops. And those are often called BLEs, or basic logic elements. And then they're grouped together into bigger things, which are called logic blocks or logic clusters. So we'll call them logic clusters to kind of emphasize that we're grouping things together into these logic clusters. And we'll look in another week or two about, well, how many things should go in a logic cluster. It's an architecture question. Not going to look at it today, but we'll look at it in a week. Okay, so that gets us to, I don't know, maybe 10 or 20 of these lookup tables and flip-flops in a logic cluster. And then we want to make a much bigger FPGA than that, so we use island-style routing between them. So we can think of this as like a very small, very simple hierarchical FPGA, and then you take that thing and connect it with island-style routing. Okay, so what do these logic clusters look like? They have some number of inputs. So again, I'm using kind of the academic notation of how do you look at these things. You have some number of inputs. You have some number of these basic logic elements, which again, think of as a LUT plus a flip-flop as being a typical one of those. We put some local interconnect in here. It's usually pretty simple. So like my inputs come in and get broadcast. I have my outputs within here. They can feed back into this local interconnect. And they're basically our programmable switches. So muxes that let me connect my inputs, choose which input of these LUTs or basic logic elements I connect it to which of these local interconnects. Okay, so I have some local routing. And then I have some inputs coming from outside. So that's coming from my island-style routing. We also usually, we have things like clocks here. So I haven't shown a clock, but now I will. And usually the clocks, we don't actually take them from the regular local routing. There's like a dedicated path in for them. Okay, so what are the positives of this? So one positive, I think Isidore's already said, is this local routing is pretty fast. These wires are short. You just go, to go from the output of one of these basic logic elements to the input of another, you go through basically one wire and one mux. And that's pretty fast. It's actually faster than island-style routing. So this local routing is fast. For small clusters. Okay, so what's a small cluster? That again is a research question. So generally it's 4 or more, and it could be as big as 32. Okay, so the most recent Xilinx FPGA actually uses 32, so a pretty big cluster. I can't make this arbitrarily big. If I just said, fantastic, let's make it 100 or 200 or 1,000, then these wires start getting long, these muxes start getting big, and it doesn't scale well. Okay, so there is a trade-off here that we'll look at in a little more detail in a lecture or two. There's a broad range that's kind of reasonable, and no general consensus on where in this range is best. Different chips are choosing different spots. Okay, so another positive of this, it still can simplify our CAD flow some. Right, that was one of the appeals of hierarchical FPGAs. It depends what your CAD flow looks like, but a natural CAD flow for this is you can do clustering. Clustering is the same as partitioning. I told you there are good partitioning tools that can chop a design into many pieces. Clustering is actually the same problem. Chop into many pieces. It's just usually when you talk about clustering, instead of cutting into 2 pieces or 4 pieces, you're talking about cutting into 10,000, right? So we usually call that clustering instead of partitioning, even though it's technically the same thing, just cutting into a lot of pieces. And usually the algorithm you use for clustering is somewhat different. It often groups things together rather than chopping things apart. So I want to make this circuit into 10,000 pieces, instead of cutting it into 2, then 4, then 8, then 16, etc. Often I just start grouping things together until I've grouped my maybe 500,000 basic logic elements into 10,000 of these clusters. But it is the same mathematical definition, just sometimes the heuristics you use are a bit different. So we can use clustering, which is a bottom-up. Bottom-up just means grouping instead of chopping. Bottom-up partitioner. Into logic clusters. Okay, why is that useful? Well, there sometimes are detailed legality constraints inside this. Maybe all these have to share the same clock. You can basically handle that in that clusterer. and kind of take care of that constraint, and then the main placement engine doesn't have to do quite as much work. We also, placement, which is the phase of the CAD flow that chooses where to put everything on the chip, tends to be the slowest. There's a lot of difficult problems in the CAD flow for FPGAs, but placement tends to be the one that is the most CPU time, okay? So if instead of telling the placer to place these individual basic logic elements, we tell it to place a smaller number of logic clusters to make its life a bit easier. And we can make it run faster. Okay, so the phase placement problem would now be like, depending on what we chose as our logic cluster size, might be 4 to 32 times slower. And we did add a clustering problem, but that can be solved fairly efficiently. And we made kind of our biggest problem, placement, smaller and therefore faster. So this can lead to faster CAD. So there's an advantage here. Although this one is a bit tricky, right? When you get into CAD tools, there's kind of like, well, exactly how do you target the architecture? The reason this one gets a bit tricky is if you actually want the highest quality, then you actually should iterate somewhat between this clustering and placement. You should allow the placement engine to make some changes. Sometimes the placement engine might say, there's a LUT in here that I really don't like. Now that I see how the placement's evolving, I wish I could move it over there. And you can get better result quality by doing that, which means that some of the simplification is now, if you want the highest quality, starts to go away, right? So, but there is generally still some simplification. And as I start doing things like telling the placement engine, hey, if you really want to, you can move one of these individual fragments, I start losing some of these benefits of it's faster. So there is, I believe, still a benefit, but it's a tricky question because you wind up with, it's kind of like I told you how the partitioning abstraction started to break down. Anytime CAD engineers can find an advantage by breaking a boundary, they start doing it, right? So then they kind of make their CAD tools more complicated, but they get more gains. Another thing is if I didn't have logic clusters, I could just pretend I had them on the chip, right? I could still take a placement algorithm, say I'll group things together, place those, and then take them apart. So you can get some of these speed ups as well, even if you didn't do it. It is a little, if your chip actually has these units on it though, you're kind of not approximating the problem as much. So it does still help you. But I guess I'm putting some caveats on how much does it help you with the CAD tools. As the CAD tools have gotten more sophisticated, maybe less than it used to, because you do so many complicated things. But another key advantage, I've shown it with clock. So I have this general interconnect, which I'm showing programmable switches on it, which means muxes. So this local interconnect is fairly flexible. It's a bunch of programmable switches, a bunch of muxes. This clock I've just shown is a clock that comes in from the general routing and it goes to every single BLE, right? I didn't put a mux here. Maybe it's hard to tell, but this wire goes to, all of these BLEs. And that's actually another positive. So it basically, I could allow every one of these basic logic elements that has a flip-flop in it to have a mux that chooses its own clock from this local interconnect. But it turns out that's probably overkill. Usually every LUT, they tend to use a lot of unique inputs, right? They won't all use the same inputs because otherwise you just get many copies of the same circuit usually. It's unusual for you to have a huge number of clocks in your design. So you will wind up with a whole bunch of registers that share the same clock. And this structure naturally lets us do that efficiently. We just say all the registers that go in this logic block, they get the same clock because that's all I built. So I saved area by doing that. Yeah?
I was just gonna ask, so if you want like a synchronizer, you need to use multiple labs.
Yeah, so I'm showing here one clock. You might, does everybody know what a synchronizer is? Some people do. Anybody not know what a synchronizer is? Does anybody who want to know what a synchronizer is? Okay, so so it's common for a clock to go to many registers. It's also common not to go to all the registers in your design. So FPGAs connect to lots of different devices, DDR, PCI Express. They have different processing modules. Even if you try to use one clock for all your processing, usually you need multiple clocks to talk to the IOs. Okay, so you wind up with different clock domains in your FPGA. Often a lot, but most of them will be pretty small near the IOs. But it's common not to have just one clock. Okay, so when you want to cross between clock domains, and if those clock domains are completely unrelated, okay, one is like 120 megahertz, one is 400 megahertz from a different oscillator, you have to design the clock crossing circuitry carefully to transfer data between those. You need to have what's called a synchronizer. So basically, data comes in, let's see if I get this right. Data's coming from some register over here on clock A. It's going to another register here on clock B. Over time, clock A and clock B will have every possible phase relationship because they're just drifting past each other, right? They're not generated from the same source. So I will eventually have this data arrive at clock B right by a clock edge. It's going to happen once in a while. That's dangerous because this register can go what's called metastable. It means that its output is halfway between 1 and 0. And basically nobody knows how to build a circuit that works where some signal here is halfway between 1 and 0 and is going through your logic. Like you can't think about that. A digital simulator is not going to simulate it. You're just going to go, what the heck is happening? So when that happens, it's going to fail. So what people do is use a synchronizer. This is also clock B. Basically, you give it another clock cycle to settle. This register, this can bounce around between 0 and 1 for an entire clock cycle. As long as it's settled down to either 0 or 1 by the next clock edge of clock B, it's okay. That's called a synchronizer. It's part of safely transferring data between two unrelated clocks. It's not the only thing, okay? But I'm not going to go into all the things you have to do. So what Isidore is saying is if you had only one clock in a logic block, this piece of this structure would have to go in two logic blocks, which is okay, right? The CAD tools will do that. But because this kind of stuff does happen, some FPGAs will say, okay, we'll let you have two clocks inside of a logic block. Harder to draw, undermines my point, therefore I didn't draw it. But the point is still, even with two clocks, you'd have a lot smaller muxes, a lot less flexibility than the pretty big muxes on the LUT inputs that select from the local routing. So I guess another positive of this, which is kind of a fundamental one, is that we can share resources that basically don't need as much programmability or configurability. Okay, so that don't need maximum flexibility. So basically, there are some signals that tend to be word wide. The inputs to a lookup table tend to be just bit wide, right? Most lookup tables are doing kind of different things, right? This is an AND gate, that's an OR gate, etc. But registers usually come from one clock domain, and usually even from one bank of registers. Like in your lab 1 and lab 2, you're working with 16 and 32-bit data. And when you have a clock, you're not clocking for all that word-wide data. You don't just clock one bit, you're clocking the whole word. So it fundamentally tends to be shared across a bunch of registers. So we get these word-wide signals. Okay, so the one I've just been talking about is clocks. That's kind of the obvious one. Right? We don't usually need 20 clocks for 20 registers. But that's not the only one. If you look at the registers in FPGAs, they also have clock enables. They often have asynchronous clear. They often have a synchronous clear, and so on. Okay, so I've got several of these control signals. As I said, this one tends to be shared across a very large number of registers, like often thousands or tens of thousands. Clock enable tends to be shared across at least an entire word, right? Like either grab this 32-bit data or don't grab it. Same thing for A-clear, synchronous clear, because this is how you're doing resets, basically. Okay, so our register actually is more complicated than we've been drawing it. It's got a D input, but it also has this clock enable, synchronous clear, asynchronous clear, and obviously a clock. And all of these signals, it's kind of overkill to give its own muxing in front of each of these to let each register pick what does it want. it's, if you just say that all the registers have to use the same ones inside of a logic block, you can save some area. Maybe that's too restrictive, but you could still say, well, they have to maybe choose between two. And that's what most FPGAs do. They build these logic clusters, and either all the registers share these signals, or they might say you can pick between two of them or something. But it's fundamentally less flexible than the regular local interconnect. It's also less flexible than if you just directly hooked up individual wire registers to the island-style interconnect, because that's fundamentally a completely flexible interconnect as well. Okay? So we get these word-wide signals here. I can think of one more positive. So what do you think? Any other positives? So I'll give you a hint. In an FPGA, do you just have logic blocks? No, that's a hint. So does this do it? And I'm only talking about logic blocks here, so why am I hinting that there might be something else? What do you think, Isidore?
When you're designing like the routing interface around things like M20Ks or DSPs, you can have the same number of signals coming in and out as you would to a logic block, or in some cases, you'll say 2 or 3 logic blocks call.
Yeah.
And then you can design one routing interface and reuse it into the other blocks, so it simplifies that.
Yeah, that's exactly right. So let me look at my notes. I think you said it probably better than I said it in my notes, so I might just write down what you said. So yeah, so basically, if you used a basic logic element and you hooked it directly up to the island-style routing, which was originally done, right? The earliest Xilinx FPGAs, that's what they did. That's very small, right? If I have a 4-input lookup table and a register, it's only got maybe 5 or 6 inputs, 1 output. It's not very big, maybe 1 or 2 outputs. And then I'm going to have RAM blocks. And most FPGAs have RAM blocks from about 9 kilobits to 32 kilobits, sometimes bigger. So that gives you, I don't know, something like 16 address bits, and usually they can do 32-bit wide words. So if you add all that up, you've got like maybe 60 or 80 or 100 inputs and maybe 40 or 50 outputs. That's a lot bigger, and the block takes a lot more area, right? So comparing doing a 4-input lookup table on a register compared to doing a 32 kilobit RAM, it's a lot bigger and has a lot more input and output signals. So that makes it actually hard to design the island-style interconnect if some of the islands are like the size of the Toronto Islands, and some of the islands are like the size of Australia, right? Like they're not that similar. They don't really they have different demands of the routing. How many signals have to come in? How big are they? So by grouping these BLEs together, we make a bigger logic unit that is more comparable in size to what we'd like to use for DSP blocks, RAM blocks, even I/O blocks. So it also helps us with our physical layout. Okay, so logic cluster is closer in size. And in I/O count. So how many signals go in and out of it to other blocks, like the RAM blocks, DSP blocks, and so on. And yeah, and what that means is it's easier to design the routing. And I mean now like the general island-style routing that goes between them. Yeah.
Well, one other kind of big positive is that when you're actually when you think of the problem the router has to do to route to it, if you have like a full crossbar like you've described there, the routing problem becomes much easier because now if you need to hit a particular LUT, you can hit pretty much any pin that's at the input, assuming full crossbar. Any of these many pins, they're all equivalent. You can meet them to the crossbar.
Yes, this is a good point. We'll get to this with routing architecture. Depending on how we design this local interconnect, but if we make it quite flexible, where it's like as you said, a full crossbar, where it can connect any input here, can now reach any input of a logic element, it actually makes our main island-style router work better. Okay, it gives it an easier problem. Instead of saying, get to this exact input of this logic element, you can say get to any one of maybe 30 different inputs on this logic block, and that's actually an easier problem for the router. So a lot of FPGAs use that technique of making the local routing quite flexible, so that they give more freedom to the island style, the router that connects the island style routing between things. Yeah.
And just have one more piece to that as well. The BLEs themselves, the lookup tables are fully commutable, so you don't need to have a full crossbar as long as you can hit any of the pins that connect. Like as long as you have a full crossbar to each of the BLEs,
Yeah.
then you're fine as well.
So these are good points, but I'm going to defer that one until we get to routing, because I think without seeing some diagrams of how does this stuff work, that might get hard for other people to understand. But you're completely right. So, yeah.
I have a quick question. I'm kind of struggling to see the hierarchical nature of that model. It just looks like it's connected together. So is that like
I guess that's a good question. It's a very flat hierarchy. I guess I'm calling this is like the first level of a hierarchy. Like all these things can just talk to each other through like one stage of switching, which matches what I showed in the first level of a hierarchical FPGA.
I see.
Now you're leading me into maybe one of the negatives here, so I'm going to use you as a lead-in. Okay, so there is a negative for these, and maybe this is okay. So what's happening to wire delay as we shrink to smaller and smaller process nodes? Like hint, it's not good. Okay, so as we go to smaller and smaller process nodes, our R and C of wires, resistance in particular, is increasing per unit length. So that means even though the wires get shorter, because all the transistors here are smaller and can pack stuff together, wire delay still tends to increase. What's happening is basically what used to be considered a short wire may not be considered so short anymore. Like this used to be a short wire, it was quite fast. You'd never consider putting a buffer in it in the middle. Doesn't make any sense. The wire delay is low. You shrink it a couple process generations and suddenly that wire looks maybe not quite so fast anymore. Maybe putting a buffer in the middle is a good idea. So basically, even short wires now have not an overwhelming resistance and capacitance, but they have a significant resistance and capacitance. Okay, that's the thing that eventually started killing like just big hierarchical FPGAs. So it's delayed for many generations when you make such a small hierarchical FPGA, but it does start to come back, which makes you go, well, maybe even these wires that kind of span the whole height of this logic block, maybe they're getting too long. They give me this nice, simple interconnect. Everybody can talk to everybody. But maybe that means a faster routing architecture is possible. Okay, this is kind of getting ahead of myself because we'll talk about it a bit in routing architecture. But the most recent Intel FPGAs, for example, basically they start dividing up this local routing further. So they have some wires that go the whole height of the logic block, and you can use them to talk from any logic element to any other one. And they have some wires that span, I think it's like a quarter of the height of the logic block, and can only be used to talk between certain ones, like the ones at the top, the ones at the top quarter, for example, can talk with these shorter wires. And the reason they did that is because those shorter wires are now noticeably faster. Now you can think of that as essentially adding, there's multiple ways to think of that, but one way to think of that is like you've added kind of another level of hierarchy, right? If you're within a quarter of a logic block, you can talk with a short wire. If you're further away, you have to use a long wire. So it still kind of fits in the hierarchical abstraction, but it's like your hierarchy is getting a little more complicated. So I don't know if that answers your question or just danced around it. But I'm definitely not arguing this is like a complicated many-stage hierarchical network. It's been sort of one stage for a long time, although it's now maybe you could, for many manufacturers, you could maybe argue it's two stages or two levels of hierarchy. Yeah.
I completely understand. My thing is, though, the reason why we went away from hierarchy in the first place to island style was these problems that we're now seeing again, and now they're creating more hierarchy. Wouldn't it make more sense to put an island style inside an island style?
You could. I've thought about that too. I think the layout is nasty. And the other thing about island style, when you get down to it starts getting hard to think about in some ways. Here I can say I get out through one mux and back in. Okay, so you go, okay, now if I'm island style, I have a mux to get on the wires, I have a mux to get to the next wire, I have a mux to get back in, I've got 3 muxes, maybe my wires are shorter. The 3 muxes kind of hurts. So like for these small units, hierarchical seems to be a better way to think of it. You just wind up with kind of a faster implementation. But as the wires start getting longer, it seems like the hierarchical abstraction becomes quite difficult to successfully realize in any kind of performant way, and it's better to start thinking about, look, fundamentally I can build 2D structures. Start thinking about that. Yeah.
The other thing I was going to about was, can you think of like the longer wires that we have, like the 8, 16 length wires in
Yeah.
cell FPGA, often like they don't connect directly to the slower wires, and that's also another hierarchy.
That's also true, yeah.
But it's not like a strict hierarchy because it's shifted over, like where each one.
You're exactly right. So you actually are basically now, you're foreshadowing a bunch of things when we get to routing architecture. So you're right that the hierarchical notion comes back inside island style as well. But, because there are some long, well, I guess maybe I'll give a quick summary of it. There are some long wires in island style FPGAs, and the way they're connected to the short wire is typically another form of hierarchy. So I guess to summarize, like the sort of vanilla, let's cut everything up into a big hierarchy that doesn't really work anymore at scale. But circuits are hierarchical. Hierarchy is a powerful concept. We still use it to make logic blocks, and we actually are going to see that we use it some when we get into high performance island style interconnect too. Yeah.
So what you're saying is we have a hierarchy.
Your amphibious car is looking better. So maybe if you look at it through the right lens, it is the right thing to do. So let's see. Okay, so let me quickly put this on the projector. I'm going to go through a few slides quickly. Let's see. Okay. Okay, so this is I mean, I told you that island style FPGAs with this kind of small hierarchy at the bottom is now dominant. But there is variation in this. Okay, so this is a flex logic embedded FPGA. So it means they don't sell this to you as a standalone chip. They sell this to you as an IP core, and you plug it into your system on chip design. Okay, so you can put a big FPGA. Well, you would never put a giant FPGA in because you'd probably go buy that off the shelf, but you could put like a small FPGA in, a medium FPGA. I'm not going to go through the details of it, but basically this shows they have, you can buy a bunch, you can get multiple FPGA, what they call it a tile, but this is a pretty big tile. Okay, so this whole thing here, and maybe I should draw this with a pen so people on Zoom can see it better. Okay, so this is the overall structure in this particular paper. They basically have 2 logic tiles, 1 DSP tile, well actually 2 logic tiles, 2 DSP tiles. And these tiles are connected with island style routing. That's what these dashes show. But when you look inside these tiles, it's kind of like a giant logic block, okay? It's basically more hierarchy than what I just showed you. So they've got lookup tables, they've got carry circuitry, so that's their logic. They've got flip-flops. So basically you can think of that's a BLE, that's a BLE, that's a BLE, because we haven't looked at arithmetic yet, but it turns out you don't just build LUTs. We're going to add a little bit of logic for arithmetic in with them too. And then they take these logic elements and they connect them together with a hierarchical interconnect. That's what this is. So this is basically the L1 hierarchy. So these different compute units, each of which combines, I guess, 1, 2, 3, 4, like 4 lookup tables. They can take pairs of these and connect them with the first level of hierarchy. If they need to go further, they have to go to a second level of hierarchy. And if they need to go all the way down to this one, they have to go through another level of hierarchy and so on. Okay, so this is a multi-stage switch network. It's a particular kind of network called a butterfly network, but it's the same idea as what I showed you. You can talk to things that are kind of close to you through one level of hierarchy. Things that are far away, you have to go through more and more levels of hierarchy. And they use this to connect together 2,500 sixlets. So they make a reasonably big hierarchy. It's got multiple levels. This diagram shows 4. When you actually scale this up to 2,500 lookup tables, it's actually more than 4 levels of hierarchy. I think from their paper, it's more like 8 or 10 levels of hierarchy. And each of these, what they call a tile, is still small enough that even these biggest wires aren't too huge. So they claim that they get good performance from this. Okay, it's hard to do independent benchmarking, but their claims are that this is, for this size of logic tile, a good approach. Okay, so that's taking kind of the hierarchy further, but they don't try to do it for a huge chip. Once they get to 2,500 LUTs, they say, okay, now if you want to combine more of those, start stamping them out and connecting them with island-style interconnect. The dominant manufacturers like Intel and AMD do what I just showed you, right? They're doing like, for those two, they're doing more like 10 to 32 of these basic logic elements, and their hierarchy is like 1 to 2 levels, whereas this one is much bigger and many more levels of hierarchy. Okay, any questions on that? That's kind of it for architecture styles. So there's kind of 2 basic ones, and most modern FPGAs are kind of a hybrid of those 2 basic techniques. Yeah?
Here's an extra question. Is there any other ones that are kind of off the wall, paper phones out and didn't really go anywhere, or is this like?
Yeah, there are lots. So, but you'll have to ask me afterwards. There are other ones like where people like sort of move all the boundaries, say, hey, this is neither. And sometimes it isn't, and sometimes they've moved the boundaries, and you go, that's still that. You just redrew the figure, right? Kinda. So, but yeah, there are other styles, but these are the dominant ones. Okay, let's see if I can bring up. So that was kind of ending last week's lecture, so now I'm going to try to go through this one efficiently. Oops. Okay, so reading from last week. So there were 2 papers, and I strongly recommend you read at least this one. How many people read the first? It's like the first half of this. We'll just sign the second one later. Okay, so many. Okay, so I'll accept it late if you haven't done it. So sorry for those who did it on time, because this is an important one to read. I mean, I think this survey paper, if you read the first half and the second half, you pick the probably is the most. It'll give you the best overview of FPGA architecture compared to like reading a bunch of the other ones. So if you're going to skip papers, which you will, try not to do that one. So I'm giving you a little more time on that. One paper for next week it's on basically logic architecture. This is looking at a more complicated lookup table structure, among other things. It's one of Intel's commercial FPGAs. This kind of changed the dominant logic structure that FPGAs use. Still based on lookup tables, but a bit more complicated. So we'll talk about that in a week or so. Okay, so course concept map. So we are down in the deep details of FPGAs. We looked at architecture styles. Now we're going to look at how do you build a bunch of low-level FPGA circuitry. Why are we talking about that? One, I think it's interesting, like how is this stuff actually made? But if you're going to optimize an FPGA architecture, you have to know how fast things are and how big they are when you're trying to make changes. And it's very difficult to do that if you don't know how it's built. So we have to look at what are some of the ways we can build sort of some low-level structures inside of an FPGA. Okay, because we want to be able to evaluate architectures quantitatively. Okay, so when you go read papers on FPGA architecture, I'm going to quickly check the chat, see if we're doing okay here. Okay, it's all good about the live stream. So well done, Amin. Okay, so most FPGA architecture results They come from basically a complicated CAD flow and a complicated area delay estimation. You kind of estimate how big would this chip be, and you map a whole bunch of circuits to it, and you see how fast they run and how much of the chip they take, and you see if that's better or worse than existing solutions. And that is a good way to do it, right? That's actually the most accurate way to do it. But it can also be hard to validate results then. You're like, well, I'm running these CAD tools that maybe I don't fully understand. I'm running some other tools to get area and delay estimations. I don't fully understand those ones either. So to gain insight, we're going to do a simple analysis by hand, which will be reasonable, but you should try to go further if you're going to publish a paper in this area. Don't say I did a hand analysis on a chalkboard and that's it. This is my paper. But you can see, how do you build the relevant circuitry? How do we estimate its area? One of the things I want to show you is when we do that, we're going to build the circuitry of a simple FPGA, both its logic and its routing, so we can see how much area is in the logic, like the LUT basically, versus in the routing. So the island style interconnect between it. In order to do this, we're going to pick like a specific example. So we're going to choose a simple architecture, because I am doing this on the board, and it's going to take me a long time to draw these diagrams already. The logic block is not going to use those logic clusters. So I said that they're a good idea. We'll see a paper that says, this works better. But we're going to do something simpler. We're going to say just our logic block is a single 4-LUT, really small. Our routing architecture is island style, and it's also simple. We only have length 1 wires. Okay, so no wires that go longer. We have to go through a length 1 wire and then get off on a programmable switch. And we're going to build all our routing switches out of multiplexers, which is actually a good practice. Okay, there's multiple ways to build routing switches. Turns out that multiplexers are now the dominant technique, and I'll show you how we build them efficiently. Okay, so it's a simple FPGA, but it's reasonable. So this is just a graphical view of what I told you. So we have a 4-input lookup table, which means we've got 4 inputs, 1 output. We have W tracks per channel. So a track is like just where can I put a wire. Okay, so if I put 12 wires in between all of the lookup tables, then my W is 12. And I'm going to build a multiplexer. That's part of what's called my input connection block, to get from those wires into my lookup table. So I need a multiplexer to select from these 12 wires who connects to this input, and I need that for every single input. I also have to build another set of multiplexers, okay? And this multiplexer is forming part of what's called my switch block. It's basically driving this routing wire, okay? And I can take an input from a routing wire below, an input from a routing wire to my left and right, or from this logic block output. Okay, so that connectivity is enough for me to connect my logic blocks into the routing, and also to connect my routing wires to each other. So I can sort of form more complicated patterns, get things going across the chip. I want to get the area of this. So what I want is a repeatable unit. So a repeatable unit is if I take this 4-input lookup table, I take all the wires and muxes to connect to them that are to my right, all the wires and muxes to connect them to below me. If I repeat that unit over and over again, I'll get all the logic blocks and all the routing channels of this chip. So that's what I want to work the area out of. Okay, I want to get the area of one of those tiles so I can see, well, what goes into it and how do I build this? Yeah?
Really nitpicky, but it looks like you can only go right and up on this FPGA.
Let me think about that. I'm not drawing all the muxes, right? So there would be another mux here, for example. Does that make sense? So every one of these wires does have a mux on it. This one is going up. I would put the mux going down here. But so there is a mux driving every single wire, but I'm not drawing them all, okay? Yeah?
Is this analysis that we're doing the same that was done in the paper reading for the pass transistors versus the transition transistors or gates?
It's not exactly the same. But I mean, we're going to build circuitry sort of in a similar way. That one, though, used somewhat more detailed area models, like a little bit more detailed area models, and then got all the delays by spicing everything, and it actually sized the transistors and so on. So I'm doing essentially a hand analysis or hand approximation of that. But they used CAD tools to actually go and optimize the circuitry. So, okay, so to figure out the area of this, I have to say, how am I going to build the circuitry? And I just kept showing you at least what is the circuitry. I haven't shown you how I'm going to build it yet. It turns out in an FPGA, because certain structures, like a lookup table and a mux, are repeated so much that you really optimize those. Okay, you don't just basically use a standard cell and say, I'm done. We're going to actually optimize those using something called full custom design. So you basically work out what does every transistor do. So we're going to build that circuitry. Okay, and then we need to estimate the area of that circuitry once we've made the schematic. Okay, so some ways people have estimated area before is you could just, well, I could take it to a higher level. I could just say, forget this mux and this mux. I'm just going to count switches, right? I'm just going to say how many wires can connect to this pin and so on. So I'm not really going to think about the circuit implementation. I'm just going to count how many programmable switches do I have. And that's been done in some papers. So what do you think? Any strengths or weaknesses of this? Is it what do you think?
Like the wire tracks, they take both lengths, they'll take area.
Yeah, it's pretty crude. Okay, so it's better than nothing, but it's ignoring kind of wiring area. It's also ignoring, frankly, it's only a crude approximation of transistor area, because well, one of the things that can be really wrong with this is I've shown here I'm using a lookup table as my logic fabric. What if I said I'm not going to use a lookup table anymore? I'll use just an AND gate. Okay, and by doing that, I removed, well, maybe it's not a good example. I guess basically, actually, I'd forget that example. I think I'm going to give an example for later, but it's pretty crude, okay, because switches correlate a little bit with transistor area, but not that well. So we should try to do better, because there's a lot of area for like buffers, and how big those buffers are depends on how long I made my wires and all sorts of stuff. So I probably shouldn't gloss all that over. But people have done that before, but you shouldn't do it in any recent papers. Yeah?
So when you mentioned this routing area, so what should there of the routing routing? So example of the transistors.
Well, there's two, in an FPGA, that's a good question. So these wires are actually run physically on top of the LUTs as much as you can. So while I'm showing them as they're off to the side, the real layout, you try to stack things as much as you can. I'm going to assume, and this is usually true, that the FPGA is transistor area dominated. Okay, it's not always true. You make FPGAs where you run at a wire area too. So yeah, you really should check that. But the thing about FPGA routing is that I get transistors in my programmable interconnect. So I don't just have these wires, I also have this mux. And I also have this mux over here. And those require transistors and SRAM cells and so on. And that usually is the dominant area. Does that make sense? So FPGA routing is kind of different than ASIC routing. Where ASIC routing, you think wires. In an FPGA, yeah, it's not just the metal, it's also all the transistors to hook all that up. Yeah?
Don't forget the SRAM, like we have a column of SRAMs, and they're going to take.
Right, so there's going to be a bunch of SRAMs in there, so we want to keep that in mind too. Okay, so counting switches is not great. Count transistors, it's better, okay, because now it's not free to have more buffers, not free to have SRAM cells, etc. It's not ideal because not all transistors are the same size. There can actually be pretty wide variations. If you need a big buffer to drive a long routing wire, those transistors are a lot larger and take a lot more area than some of the other ones. So counting transistors better, but doesn't get everything. What about estimating the layout area? So this is where most researchers come to, is make an estimate of layout area. So you try to account for the fact that some transistors are bigger than others. A little more sophisticated still is you also try to check, maybe there's so many wires, I'm wire dominated. So that's the best thing to do. Well, it's almost the best thing to do. The absolute best thing to do is just make a complete layout, right? So lay out everything out, lay the wires out, the SRAM cells, etc., and just measure it. And now you go, it's the layout. It's like I've got the best answer. Okay, but as you could tell, I didn't seem super keen on this. I kind of like this one better. Why? Why isn't this the best thing to do? Yeah. Yeah, it takes forever. Okay, so if you don't care about time to graduation, for example, go tell your advisor that you just learned the best layout estimate, the best area estimate for FPGAs, and you want to do FPGA architecture research is lay it out. So you've got like 150 ideas, you're going to lay them all out, and you will graduate in 2150, okay? So it just takes too long. You can do this, commercial FPGA manufacturers do this for bits of the architecture as they approach their final decisions. They can't actually do it for all the architecture decisions. Even in the big companies, they use layout area estimators through most of the architecture design process. But they can afford to kind of micro-tune and cross-check on a few final candidates. Academics, yeah, usually, no, I'm not going to do that. There's also an issue here of even if you said, I'm willing to spend the next 30 years laying out architecture candidates, how good is your layout, right? Maybe you got bored after year 12. And your layouts started getting not as optimized as they could be. Because you don't just want a layout, you actually want a pretty optimized layout, which is even harder to make. If you're not going to spend that much time optimizing it, you're probably better off to just try to estimate how good could an optimized area layout be. So this is where mostly we go. And then there are a few different models that make different trade-offs, trying to get more accurate answers here versus being easier to use. So the one that we're going to use, which is pretty widely used, is called the minimum width transistor area model. I gave it this name years ago. It probably is not a fantastic name. I don't actually know exactly why I called it that, except it's quite literal. What it does is it basically, it's essentially an abstract, it's like a quick estimate of layout area. So if we have a transistor in every process technology, there's like a minimum size transistor we can make. Okay, so we make the width as small as we can, or if it's FinFET, we make the number of fins 1. Okay, and we make the transistor length as small as we can, like the channel length. We want to actually connect to it. So this is our gate, this is our source, this is our drain. So we need to have like contacts so we can actually connect something to it. And we've made this as small as the design rules allow. And then we also have a minimum spacing to the next transistor vertically and a minimum spacing to the next transistor horizontally. And this is now a repeatable unit. I can make these small transistors over and over and over again, and I can actually connect to them. Maybe I'll have some trouble higher in the metal stack running everything, but at least I know I can connect to them all. So we call this gray box, that's just like the minimum width transistor area. Smallest transistor I can make that has the right spacing to other transistors and that I can actually connect to. And some of the transistors we're going to make, we'll want to make bigger. And there are a couple ways you can do that. You can widen the diffusion. Okay, so just make a transistor wider and it gets twice the drive strength, twice as much current basically for certain voltage. That's a bulk transistor. It's very similar though in FinFETs. In FinFETs you just make 2 fins, which is the equivalent of making the transistor wider, and it has a very similar effect on area. We can also put essentially 2 gates in parallel. So if I hook this to my output, for example, and this to the same input, this is like 2 transistors in parallel. So it's another way to get twice as much drive strength. And basically the key thing to notice is neither of these doubles area. This increases the width, but it doesn't increase the spacing to the other transistors. This basically takes, we would have had that structure to get 1 transistor. If we put on this additional second input that's connected to the same thing, we get twice as much drive strength, but we added, maybe 50% or less area. Okay? Does that make sense? So, and you can fit a very simple equation to this that is basically the area to get a certain drive strength. Okay, so 1 is just like the minimum drive strength, the smallest transistor you could get, is like 0.5 plus 0.5 times the drive strength. So it just means the smallest transistor you can make, drive strength of 1, has an area of 1, right? That's the minimum. If I want to make it have twice the drive strength, because I need it to charge up a capacitor twice as fast, it has an area of 1.5, and so on. People have improved on this. So the paper that I assigned last week has a more accurate formula, but it's a bit more it's not very complicated, but it's not quite so simple as this, but it's a bit more accurate. And then there are other papers that have gone and done layout studies where they've come up with even more accurate formulas. They follow the same idea, of let's work out how big the transistors are and how we'll hook them up, but we'll use somewhat fancier equations. For this chalkboard exercise, I'm going to use this nice simple equation, which isn't too far off, and it's a lot easier for me to compute on a chalkboard. But if you had a paper on this, I would go, check out these papers to get somewhat better estimates. Okay, so I'm going to do a simple island-style FPGA by hand on the chalkboard now. Okay, so let me turn off the projector. Any questions on that? It's all pretty clear? Okay, I'm going to take that as a yes. Let's see. Okay, so we're going to start building like all the circuitry of this simple FPGA. So first thing we need is a lookup table. And maybe I'll start it over here. Okay, so lookup table, I told you already, is basically made out of SRAM cells. So I'm just going to show you a little lookup table here. Okay, so that's my symbol for SRAM cell. And then we build a mux tree that lets us select, based on our inputs, we'll get the right SRAM connected to our output. And this structure is really crucial in FPGAs, so they build it full custom, right, out of individual transistors, not typically out of standard cells. Okay, so what does it look like? So I basically connect a pass gate to every one of these SRAM cells. And here's my first input. We'll call it input 0. And let's see, it's going to go in and it's going to control that one. And it's going to control that one. And I'm also going to invert this. So I got an inverter here. And I'm going to use the inverted version to control two other ones. Okay, so hopefully that's legible. Yeah, so good question. Okay, so let me start with pass gates. You can ask that question again at the end, okay? Okay, so what have I done so far? Now let me hook these together. Okay, and then we basically short the outputs of pairs of pass gates together. Okay, so hopefully that's legible. Maybe I'll just use solder bumps. Okay, so basically this pass gate or this pass gate will be on, right? Because one is controlled by input 0, one is controlled by the complement of input 0. So only one will ever be on. I can short the two of them together, and I'm going to get either this SRAM cell or this SRAM cell. Its value will be copied to there. Same thing here, okay? And then I just repeat the structure again. So make a pass gate here, make a pass gate here, and control that with input 1. So input 1 will control this one. Well, the complement version will control that, and the true version will control that. Short these together, and that becomes my output for like a 2-input lookup table. So if I need more inputs, I just repeat the structure downwards. Like for one more input, I'd copy this whole structure downwards, and then add one more level of input. Okay, so every input I add, basically going to double everything, because I got to copy this whole thing down and add another layer. So Does that make sense? Let's see. So this signal is weak. So I want to send this out to my local routing, for example. So I want to be able to connect it to muxes, be able to connect it to routing wires. I want to make these transistors small because I've got a lot of them. Okay, like this, if I make a big lookup table, a 4-input lookup table, I have a lot of these pass transistors. We'll count how many in a minute. So I would like to make these quite small. And small transistors have high resistance. Okay, so basically that drive strength is like the inverse of resistance. And I would like to make these low drive strength if I can. And then when I have transistors in series, I effectively add their resistance. Okay, so these two transistors in series mean it's going to be slow at discharging large capacitances. The time constant, again, of a circuit is RC. So if my R is high, I do not want this C to be high. Okay, so, and connecting this directly into a bunch of routing muxes means a bunch of wiring, a bunch more transistor diffusion hanging off of this is going to get a lot of capacitance. Don't want to do that when it's going to be that capacitance times a fairly large resistance that's going to give me the delay of the LUT. So I need to protect this fairly weak signal from that downstream capacitance. So how do I do that? Yeah, right. So we put a buffer in. So I'm going to put a buffer in here. So I put an inverter, and this is now my output. Okay, so I just made a 2-input, 1-output LUT. There's still something missing from this. Okay, so if you remember your 231 well, there's something a bit dodgy about this still. So what else do I need? Yeah?
I'm not sure if we're looking for a level restore.
Yeah, I need a level restore. So, okay, so I use pass transistors here because it's very area efficient, right? I'm using one transistor that either connects or does not connect this SRAM cell to this node. So I can't really make anything smaller than that in a standard process. It's like one transistor switch. An NMOS pass transistor, an NMOS transistor can transmit a logic 0 well. Okay, so if I put a 0 here, this will go to a 0. Okay, it'll go to 0 volts. So that's good. An NMOS pass transistor, can it transmit a logic 1 well? See if you guys remember this or not. What do you think? Can it transmit a logic 1 well, this pass transistor? What's that? Yeah, the transistor shuts off when its source, let's see, well, basically when its source and drain are within a threshold voltage of the gate, it shuts off. Okay, so the gate is at, say 1 volt, if this is a 1 volt process. This cannot rise to 1 volt. Okay, this can be a 1 volt, this can be 1 volt. This is now my source, basically. It's like my lowest voltage node. When this is equal to 1 volt minus VT, it's off, right? Remember, you have to have the gate voltage must be higher than the source voltage by a threshold for the transistor to be on at all. Okay, so this drops a threshold voltage, maybe 300 millivolts in a 1 volt process. So maybe this signal makes it to 0.7. Doesn't make it all the way to 1. If I send that into this inverter, that's really bad. Okay, it's really bad because this inverter inside of it has a pull up and a pull down transistor, and they'd both be partially on, right? Like, it is not good to send intermediate voltages like this into inverters because they're going to leak like crazy. So the inverter will produce, if you send in a 0.7, it's going to produce an output that's about 0 volts. Okay, because it does, it's nonlinear, right? This is enough that the output will be pretty close to 0. But you have a problem of this is going to leak like crazy. So what we have to do is put a level restorer in. And the cheapest level restorer is we just put in a small PMOS that's connected to this node. Okay, so if this is a logic 1, let me think about this. Okay, so this is a logic 0. Yes, this is a logic 0. This turns on, okay? And it pulls this all the way up to 1 volt. Okay, so this will slowly rise to 1 volt, and that will stop the leakage. If this was a logic 1, this turns off and just doesn't do anything. Okay, and that turns out to be exactly what we want. So If I've got a logic 1 here, this just goes away. It's shut off. If I've got a logic 0 here, it starts pulling up this node till it gets all the way to 1 volt. Does that make sense? You need to make this, well, how strong do I want that to be? Yeah.
If you made it too strong, you'll never be able to turn it into a 1.
Yeah, so this is sometimes called a weak keeper. It's a level restorer or a weak keeper. It can't be too strong. So you make it the minimum width, and usually you lengthen the gate, okay, so that this is actually quite weak because it needs to be overpowered by these pass transistors. If this is holding this value at 1 and you change your inputs, so a new SRAM cell is selected and is making it to the output, these 2 pass transistors in series have to be more powerful than this so they can pull the signal down to a 0 and the output can switch. That actually helps us make this reasonably small. So we definitely want small width. Like I said, even often you need to make the length a bit longer to weaken it further because you want it overpowered. Okay, so that is like kind of introduction to pass transistor logic, which FPGAs use a bunch. So pass transistor logic is a dangerous design style. Standard cells generally do not use it because of stuff like this. Doesn't pass a logic 1 very well, so you have to put like weak keepers in. The delay through this is a little more complicated because we have multiple transistors cascaded together, etc. But it's a very efficient design style to make multiplexers. And this LUT has an embedded multiplexer, and we're going to repeat this like 1,000,000 times. So FPGA manufacturers do put the extra effort in to use this dangerous design style in order to make things smaller. Does that make sense? Now, Isidore asked a good question. He said, what about transmission gates? So does anybody, who knows what a transmission gate is? And it can't be Isidore, because he asked the question. Well, actually, if you don't know what a transmission gate is, that's okay, I guess. But anybody else know? Let's see if we can hear from somebody we haven't heard from. What is a transmission gate? If not, I'm going to just go back to somebody we have heard from. So Hale, I saw you put your hand up. What's a transmission gate? Right. So a transmission gate is, let's see, I'm really bad at drawing. Okay, let's do this better. It's basically this structure, okay, where I connect the same thing to, okay, so I short the input of this transmission gate together, of this PMOS. Okay, here's my source and drain of an NMOS and a PMOS, and basically I short the source together, the drain together, and I actually connect the gates to like the opposite. Okay, so if I wanted it on, this would be a logic 1, this would be a logic 0. And now they're basically working in parallel. This will transmit a logic 0 well because this can transmit a logic 0 well, and it will transmit a logic 1 well because this PMOS can transmit a logic 1 well. They have, if you actually go through your transistor equations, you'll see they have the opposite behavior. This NMOS cannot get, it degrades a logic 1. This PMOS degrades a logic 0. Together, they don't degrade anything. So this is the alternative, right? Instead of using these pass transistors, just the NMOS, you can basically, everywhere where I have a pass transistor, you can replace it by this 2-transistor structure called a transmission gate, and you can get rid of this. Okay, you can say, I have a safer design style. I don't need that anymore. And because voltages are getting smaller and smaller to control power as we go to more recent process technologies, threshold voltages are also getting smaller, but not quite as at the same rate, because if you make the threshold voltage too small, you get too much leakage. It means that historically, FPGAs have used pass transistors, but in the latest process nodes, they usually use transmission gates. They'd like to use pass transistors. They actually would make the chip smaller, but if you drop too much voltage, it gets too hard to make it reliable, and it also can start becoming slow, right? Like if these are too bad at doing a logic 1. So in the latest process nodes, this is typically what you do. It doesn't change any of our analysis, though. It kind of multiplies a bunch of things by 2, and it makes all my diagrams twice as complicated, and they're already hard to draw on a chalkboard. So we're going to do this, which is dominant in older process nodes, right? And older is not really old, you know, maybe 28 nanometers, 22 nanometers. So around 14, it's debatable, and around 10 and 7, you would probably go to this. So both are used. There's kind of just a switch point. And the second reading from this week actually talked about that. Okay, so hopefully you're all with me. You understand how that was built? Okay, so let's look at, what I want to do now is I want to count as transistors. So how many transistors are in this? Because that's why we made this schematic. So the number of transistors is equal to, this is my 2-input LUT, so it's pretty small. I've got 4 SRAM cells. I'm not going to draw this out, but an SRAM cell typically, there are multiple ways to build them, but typically it's going to take us 6 transistors. So I've got 6 transistors for each of those. And in my 2 LUT, there are 4 of them. Then I got to add in my pass transistors. I've got 4 in the first stage, 2 in the second stage. So I've got 6 pass transistors. Okay, then inside my inverter, well, I've got 1 inverter, 2 inverter, 3 inverters. Each of them takes 2 transistors, so 3 times 2. And then I've got that 1 keeper. Okay, so this is inverters. This is my level restorer keeper. Okay, so that's equal to 37. In general, if I have a k-input lookup table, because 2 is not very big, this would just be 6 transistors for each SRAM times 2 to the k. The number of pass transistors is a geometric series. The first level is 2 to the k, 1 connected to every SRAM. The next level is half that. The level after that's half again, and so on. So if we add up that geometric series, it's just 2 to the k plus 1. And normally it would be minus 1, okay, if you remember your geometric series formula, or you can rederive it on a piece of paper if you like. But we leave off the last transistor, right? The geometric series would say you have like 4, then 2, then 1. Well, making 1 pass transistor that you always turn on is kind of useless, or worse than useless, so we leave that one off. So we get 2 to the k plus 1 minus 2. Okay, then we need our inverters. The number of inverters we have, well, we have 2 transistors per inverter, and we need k of them for our inputs, plus we need 2 more for the output inverter, plus we need 1 transistor for the keeper. So we get that, okay? So that's our formula. We're going to be dominated by these terms for big K. So this kind of matches what we talked about a couple lectures ago. It's exponential in K. So we kind of now have more proven it that this is exponential in K. So you don't want to make giant lookup tables. It kind of reiterates that. Okay, I said transistor counting is reasonable. Like it's better than some other area models, but we could do a bit better by trying to estimate how big each of these transistors are and then estimating their layout area. Okay? So if let's say I use a 4-input lookup table, because that's what I said we do. It's more reasonable. And let's say that I can use the smallest transistors possible that give me that 1 minimum width transistor for the SRAM cells. That's usually pretty much true. In the SRAM cells, you can use pretty small transistors. And let's say I can also do that for the inverters. But these pass gates, to make them strong enough to overpower this weak keeper and to make sure that this doesn't get too slow, because this is actually my timing critical path, we're going to say the pass transistors are bigger. So we'll say the pass transistor size is equal to 5 times minimum. Actually, let's not say size. Let's say drive, because size is ambiguous. Okay, so I want to make them 5 times as powerful. Okay, so 5 times as wide, or some of those other tricks. I'm not going to type all this in, but if I take this and put it into my minimum width transistor area formula, I get an area which is equal to 217 minimum width transistor areas. And I didn't do anything very magic here. All I did is, this is 1 area unit. If these pass transistors are 5 times minimum drive strength, I'm using a very simple formula of the area is 0.5 plus 0.5 times the drive strength. So each of these are 3 units. Each of these is 1 unit. Add it all together, I get 217. Yeah.
One thing, maybe just semantics, but when you think of the actual like shape of the layout, right, it needs to be sure it's a square, otherwise it's not going to work. We're going to repeating unit.
Yeah. So you're saying, well, this would be kind of a funny shape, and maybe you're going to get a lot of white space, which is true. I'm not kind of saying how it's laid out, though. I am leaving that as an exercise for the reader. So the fact that I drew it this way doesn't mean you have to lay it out this way. And in fact, you usually do fold these back on themselves and so on. So for example, I could take the next lookup table. Like this would be one simple technique. I could mirror the next lookup table. If this turned out to be kind of a wedge shape, do one lookup table this way, but I'm actually going to do it, if I was doing another lookup table in a larger logic block, I could flip the next one. Now that actually turns out to be a little more of a mess, so I probably won't really do that, but I can basically sort of fold this layout back on itself. What's that? Yeah, so the way Intel actually does this is they have columns of things, but there are other ways. You can flip it, and they do sort of flipping inside that and look at it a lot. So, that's when you get into more detailed layout area models, they try to sort of predict some of those things. It is very hard, though, because layout's tricky. So one of the FPGA architectures that I worked on, I think it was actually Stratix 2. David Lewis, who was at the time like Altera's kind of chief FPGA kind of fabric architect, and he was on my team, so he reported to me. He came up with just a different way to do the layout of multiplexers. Okay, so he just kind of folded. I don't know if I can even still to this day explain it to you entirely, but he effectively rotated everything by 90 degrees, did it all differently, and called it the super horizontal building block. And it basically cut the layout area by 27% of a mux. Which is kind of insane, right? But he just basically reoriented how he was doing all the transistor folding and so on. So it can be hard to model, do you know what I mean? Because before him, the layout area for that key structure was like 27% bigger, and then he figured out a way to pack it more densely. So this just kind of sidesteps all that and just says we at least know bigger transistors and more transistors will take more area. Generally, when you get this area, you care about relative area. So you can, if you want to turn it into a real area, you would normally multiply by a bloat factor. Say my layout engineers, that's probably too hard. Let's multiply everything by 1.5. But if we're just trying to compare architectures, that 1.5 doesn't really matter. Does that make sense? Yeah. So K is the number of inputs. Okay, so let's say, so maybe I should write K input LUT. Okay, so I'm basically getting here, how many transistors do I need for a K input LUT? And then here I'm saying, well, I'm giving you a simple example of they're not all the same size. The SRAM ones I'm saying are minimum size, so they take 1 layout unit. The pass transistors are often made a bit bigger, so I'm saying make them 5 times the minimum drive strength, which means in our area model they'll take 3 layout units. And I'll keep these ones still minimum. And under those assumptions, I would get this area in kind of this minimum transistor sizing unit. And if I was doing this more carefully, I'd actually go spice this and so on and actually figure out how big everything should be. And the second reading from this week was actually a CAD tool to help you do that automatically. So everything that I'm doing on a whiteboard, if you go, wait a sec, you can't just do that on a whiteboard. You're totally right, okay? Like you should use tools to go optimize this. But I can kind of guess, and my guesses are reasonable, so that we can kind of move forward. So I think with that, we'll take a break till 5:40. So maybe if you have other questions, you can ask me during the break. Okay. inputs has a mux in front of it that chooses which routing wire we're going to connect into it. Okay, so how big is that mux? Well, that's an architecture question. I'm going to say it's 16 to 1. Okay. So I can choose from 16 different routing wires passing by me which one connects to this LUT input. Now I should actually confirm that's a good number with CAD tools and so on, but this is a reasonable number. Okay, so how can we build that? So the first way we can build it is what's called a one-level mux, or I call it a one-level mux. It looks a lot like what we just built for a lookup table, except it's just the mux part, right? So it's the mux part of a lookup table. That's what we're building now. But in the lookup table, we basically built a tree. Okay, we built the one stage kind of cut us from four SRAM cells to 2 values. The second stage cut us from 2 values down to 1. So it was like a tree of making decisions. In the routing here, I can do it all in one level if I want. Let me show you what I mean. Okay, so I've got 16 inputs. So I've got input 0. I hook that up to a pass gate. And I control that pass gate with an SRAM cell. So in the LUT, I was controlling my pass gates with inputs to the LUT. In routing muxes, I'm going to control them with SRAM cells that the CAD tool programs. The CAD tool is going to decide, does input 1 go through this mux to the LUT input or not? Or input 0. And I'm going to do the same thing for input 1, right? So it's got another SRAM cell that controls it. I'm going to short those together because the CAD tool is only going to turn one of these SRAM cells on. All the other pass transistors will be off. Okay, I'm going to repeat this down to here. And I've got input 15. Same idea. An SRAM cell controlling it. Short all those together because only one will ever be on. Just like before, my pass transistors are not good at passing a logic 1. So I put the same, and they're kind of weak. So I put the same structure on. Put an inverter here so that I can drive into the LUT. I don't have to worry about having a bunch of capacitance slowing this down, so I put an inverter to isolate it. I know that this node is not going to transition cleanly to a logic 1, so I put my weak keeper on, or level restorer. Okay, and I get that structure. Everybody with me? Sound good? Yeah.
I just want to confirm, so the difference between this structure and the previous, because the previous one that's using the LUT, the inputs can be 1, 1, 0, 1 or something like that, but
Yeah.
in this one, the SRAM cells, only one of those SRAM cells could be on.
Right. Yeah, that's exactly right. So the CAD tool can make sure so let's say this one is a 1. Then the CAD tool will put zeros in all the other ones.
I see, that's a lot of sense.
And you're right. In the LUT, we couldn't do that because we're just bringing in essentially encoded input. We just bring in inputs, and we're directly using them to control the mux. So we kind of had to build it in sort of a tree structure so that one input could control one level of the mux. But we don't have to do that here. The CAD tool can just figure out, that's what I want. Turn this one transistor on. Okay? Does that make sense? Okay, so I'm going to count how many transistors this is. Okay, so first I need SRAM cells. And I told you that an SRAM cell typically takes 6 transistors. So we've got 6 transistors for the SRAM cell. We've got 1 transistor for the pass gate. And that's basically a repeated structure. Okay, so this is SRAM. This is the pass gate. And I got to multiply that times the number of inputs. Okay, so in this case it was 16, but this is a general structure. So I multiply that by the number of inputs. And then I've got a little bit at the end. I've got 2 transistors inside this inverter, and I've got this weak keeper, so it's another 3. Okay, so that's how many transistors I have. The SRAM cell is going to be small, like those transistors can be kept small. This is going to have a reasonable load on it because this wire can get a bit long. Okay, these are all connected to different routing wires, which means that they may not be able to get all these pass transistors right beside each other because they're all trying to connect onto different routing wires. And there are 16 of them, so this wire can be somewhat long. and there are 16 transistor diffusions hanging off of it. So for that reason, I'm going to say that I need to make these a bit stronger than the minimum. And to make the math easy, I'm going to say I make them exactly as strong as I did before. So I'm going to say the drive strength of the pass transistors is equal to 5 times the minimum. All right? In my simple area equation, it's simple, but it's not bad. The area of a transistor, of a 5 times drive strength transistor is 0.5 plus 0.5 times 5, which is just 3. So this is 5 times stronger, but 3 times bigger than the really little transistors in the SRAM cell. So my area of the transistors is going to be 6 for the SRAM, plus, I'm going to plug in my area equation, 0.5 plus 0.5 times 5, or 5 divided by 2. I multiply that by the number of inputs, which in this case is 16, and I add those last 3. Okay, and I get for area is equal to 147. And I'm just going to call those minimum width transistor areas. Okay, so that's for 16 inputs. Everybody with me? Okay, so it's like this is some complex algebra. We've got like addition, we've got multiplication, we've got order of operations, but I feel you're all with me still. I think I'm actually the most likely one to screw it up, but I'm sure you catch me. Okay, so what's interesting about this? 147 minimum width transistor areas. How big was the LUT? Anybody remember? Yeah, actually has very good memory. You got it exactly right. Okay, so this mux, how many of these muxes do we need for this LUT? So do we need 1, 2, 6? You need 4 of them, right? So we need 1 in every single input. So what does this tell us? The size of these muxes that connect our LUT inputs to the routing, these 4 together are already going to be significantly bigger than the LUT. So it's telling us that routing area matters a lot. Okay, don't neglect routing area. Yeah.
For this pedantic, how big was our trunk? Because if we're making these 16:1 muxes, we have the permeability in the mux. We almost certainly, for this small architecture, would not be having 16:1 muxes.
It's possible. It makes my math easy.
But relative to the LUT and the architecture that you've created, like you're way over provisioning.
Hold that thought, and maybe we can get back. I don't think it's wildly over, because this may be more advanced than other people can handle right now. But for a small logic block like this, you actually tend to have these muxes cover most of the channel, because you don't get, it's kind of easier to get blockages. So 16:1 is not unreasonable in it. You could, I think what Isidore is saying is he doesn't like my architecture. He's like, I think it would be more optimized if you chose 8:1. And it might be, but now we get into a complicated question of we need to run the CAD tools, see how well it routes, see if we need to make the channels wider. There's like all sorts of like coupled effects. So I'm asserting 16 is broadly reasonable. Isidore is asserting that somewhat less would be broadly reasonable. We're probably both right. And without CAD tools, we can't really resolve the argument any better than that. Does that make sense? Okay, this is one way to build a mux. So I notice I called it a one-level mux. Another way we could build a mux, I don't know if I want to draw this whole thing. Maybe I will quickly. So we could do a K-level mux. Okay, so what does a K-level mux mean? It's basically what we built in the LUT, right? So we don't have to build it this way, where essentially we have just one pass transistor. It looks a little more complicated. Let's see if I can draw this properly. So I'm not going to draw all 16 inputs, but you basically can say, okay, let's take my first input. Goes into a pass gate. We're always using pass gates. And we're going to control it with an SRAM cell. And we're going to say that SRAM cell, inside an SRAM cell are cross-coupled inverters. So you actually generally have access to both the true and the complement of what's stored inside the SRAM cell. So I'm hooking the true signal, which I'm calling S, up to this gate. Okay? I go down to input 1 and make another pass gate, and I'm going to hook it up to the opposite signal. Okay, so the S bar. So one of those two will be on, but not both. Okay, and let's pop that over. And I'm going to repeat this, maybe another iteration of this. Okay, so input 2 is going to get the same structure. Input 3 is going to get the same structure. So basically, I'm going to take, let's see if we can draw this neatly. Okay, and let's take this signal down here. Okay, so I just repeated this structure, right? So basically, this one's controlled by the true value of this, and this one's the same. This one's controlled by the complement. It's just the same trick I did with the LUT, except this, instead of being a signal, it's an SRAM cell.
What's the label for that thing?
That says S.
No, not that.
S and S bar.
The level. What level?
Okay, that's supposed to be a K level. Okay, so that's my, let's see, what else do I need to do here? So let's go over this. Let's go over this, go over this. Okay, these get shorted together. It's my basic structure for building a tree-based multiplexer. And let's put solder bump on that. Okay, then let's repeat this structure. This again, just like the LUT. So I'm going to put into another pass gate here, another pass gate here, make another SRAM cell, control with the true, one of them, control with the complement, the other one. Whoops. And I'm going to take these and short them together. And that's going to go on to the next stage. And dot, dot, dot. Okay, so for a 16:1 mux, I need 8, 4, 2, 8, 4. I need 4 stages of this. I need, 16, 8, 4, 2. So I need 4 stages of this to get it all the way down. And at the very end, I have my favorite structure, an inverter, and this weak keeper. Okay, so what have I done? I've basically added more pass transistors, because this actually has more pass transistors than this one had. Because I have just as many pass transistors in the first stage as I had over here. And I have more pass transistors in some subsequent stages. But I have gotten rid of some SRAM cells, right? Here I had 16 SRAM cells. Here I'm only going to need basically log base 2 SRAM cells. So let's just move this down. Okay, so let's count the number of transistors in that. So the number of transistors is equal to log base 2 of the inputs, okay? Because the number of stages is logarithmic. Each of them is controlled by exactly one SRAM cell. Okay, and that's multiplied by the number of transistors in a SRAM. So this is my SRAM count, or SRAM transistors. And then I have to do exactly the same calculation I did for the LUT. If I add up all these stages, it's a geometric series. That geometric series is equal to 2 times the number of inputs minus 2. Because if you remember geometric series, if you like, wait, it should be 2 times inputs minus 1. But there's one pass transistor missing because we don't put a pass transistor that's always on in. Okay, and then we have this last thing of okay, so this is our pass transistors. And this is our final inverter plus the keeper. Okay, so if our inputs is 16, and we're going to say that these pass transistors, again, this is on our critical path. You know, we hook these up to routing wires. The signal comes from a routing wire, goes through all these pass transistors, and goes into this buffer and onto more routing wires. So this is a speed critical path. We're going to make those transistors a bit bigger. So we're going to say, again, the drive of the pass transistors is equal to 5 times the minimum, which we know makes the transistors 3 times as big. If I substitute that in here, I get an area of 123 of these minimum width transistor areas. Okay? Which is a bit better than what I had before. So it's a bit smaller than 147, but maybe not as much smaller as I'd like. Yeah, any trade-off here, though? Go ahead.
I was gonna, you can comment on the critical path, like on the delay. You have more muxes, but the capacitance is gonna be less on each of those terminals. So it's not clear to me which one would be.
Yeah, generally this one will be slower. Okay, so I did save some area, but maybe I saved 15% area, so it's not an overwhelming savings. And the speed is slower. Okay, why is it slower? Well, if you want to know exactly how much slower, you spice this. But again, we can pretend a transistor is like a resistor, because it is. It's a nonlinear resistor. So when it's on, it behaves like a resistor. We got 1 R, 2 Rs, 3 Rs, 4 Rs, 4 resistances in series that are discharging whatever capacitance is here. But as Isidore said, this final capacitance maybe is smaller, makes it a little bit more complicated, versus essentially one resistance discharging a larger capacitance. That's why I say you can't do this perfectly. In practice, this one works out to be slower. Okay, the fact that some of these capacitances are smaller because it's more local is not enough to compensate for the fact that we have 4 transistors in series, and this will be slower. Does that make sense? Okay, but there's another way you can build routing muxes. And can you think of any other ways to build it? Okay, so we got 2. So this is basically like essentially a kind of a tree-based structure, or fully encoded. This is a decoded structure. It's like a one-level flat structure. Yeah? Yes. So, and this one is not, spoiler, it's not an amphibious car. Okay? This is like another case where you wind up with a good option in the middle. I mean, this is used. So both these techniques are used. So in FPGAs, muxes are so common, like routing muxes, that you do spend a lot of time micro-optimizing them. So this is used. Sometimes that is used. But the most common one is what I'm about to show you. So let's see. Let's go to this one. Okay, so the last option I'm going to show you is 2-level mux. So a 2-level mux is actually the hardest one to draw, so I usually screw it up when I draw it. Like I start drawing lines all over the place, and it turns into a rastas. So I'm going to try really hard to follow my diagram. But let me give you the basic idea. The basic idea of it is relatively simple. You cascade 2 1-level muxes. Okay, so here we did in one step. We muxed from 16 inputs down to 1 output. Okay, we're going to try to do that in 2 steps. So for example, for 16 inputs, we're going to mux down 4 to 1, and then again 4 to 1, which multiply together is 16. So that's looking good. This doesn't sound like it's really, you go, well, wait a sec, this sounds an awful lot like your tree-structured mux again or something. I mean, that doesn't sound very interesting. But the second thing you do is you realize that you can share SRAM cells across the first-level muxes. Okay, and let's see if I can draw this properly. I need a lot of board space for this. Let's see what I got here. Okay, so I'm going to attempt to draw this very carefully so I don't screw it up. Okay, so this is this is 4 pass transistors, and I'm going to actually control their pass gates with 1 SRAM cell. Okay, still seeming somewhat legible. Put some solder bumps in here. Okay, so this SRAM cell turns on all 4 of these pass transistors as a unit. So they're all on or all off. The CAD tool is going to program what goes on there. Okay, I'm going to repeat this 4 times. Okay, so I'll just show you the last part of the fourth one. So down here, there's an input 15 and an input 14. And they also go into pass transistors. And they're controlled by, an SRAM cell. This SRAM cell will also be controlling 4 pass gates. I'm just showing 2 of them. Okay, so I basically take this first one down here, take this second one down here, take this third one down here, and this third one matches up with the second last. I'll take this fourth one here, and it matches up with the last one. Okay, so I'm not drawing the whole thing, but basically I'm making kind of a 4-bit bus here. Like there are 4 signals here coming out of these 4 pass transistors, and in 0 is going to be shorted together with the pass transistor that is connected to in 4, in 8, in 12, etc. Okay, every 4th one. And then, so this basically forms 4 4-to-1 muxes that are all that are controlled by the same 4 SRAM cells. Okay, all in parallel. And then I take each of these 4 signals. So I take that one, that one, that one, whoops, and that one, and I put them all into another set of pass transistors. And each of these is controlled by its own SRAM cell. And then I short all those together, and I put it in my favorite structure, the inverter and the weak keeper. Okay, so that should be pretty obvious. This is just a 4-to-1 mux, right? 4 pass transistors controlled by 4 SRAM cells. That's a 4-to-1 mux. This structure that is always challenging my ability to draw is essentially 4 4-to-1 muxes, each of them controlled by the same SRAM cells. Okay, so it's like 4 of them in parallel. So what does this do? Okay, if my input was, say, input 1, that's what I want to make. This routing wire is the one that I want to make it to the output. Okay, the CAD tool has determined that's the right choice. Then what the CAD tool is going to do, let's see, let me pick one of these. Yeah, so let's say that, let's say input 2 is the one that I want to make it out here. Okay, so the CAD tool is going to say, okay, it's one of these 4 inputs, so I should put a 1 in this SRAM cell. And that's going to copy these 4 inputs onto these 4 intermediate wires. It's going to put a 0 here, and it's going to do that in the other 2 copies. So now this signal here, this wire is connected to input 2, so the CAD tool is also going to put a 1 here. And I'll put a 0 there, and a 0 there, and a 0 there. So that copies this onto here. Okay, so it works. We also basically connected in 0 to this wire, in 1 to this wire, in 3 to this wire. We don't care about any of those. They all get connected because they're all listening to the same SRAM cell. And that's essentially the trick that we're using here. We're building a 2-level mux, but also realizing that we can share some SRAM cells because we just don't care about some of these when we don't need them. So we don't need to make, normally you would make a separate SRAM cell for every one of these pass transistors, but we don't need to do that because we can basically select a whole group of 4 by using one SRAM cell, and then we'll choose which of those 4 was actually the one we wanted. So we're kind of exploiting don't cares, right? The fact that there's some redundancy if we were to make a separate SRAM cell for each one of these, and that allows us to reduce the number of SRAM cells. Hopefully that makes sense, okay? If not, kind of go, well, that works well. Two-level muxes work well in FPGAs. If we add up the number of transistors here, we get, okay, so how many SRAM cells? We have 4 in the first stage, 4 in the second stage, so we get 4 plus 4 SRAM cells. And each of those takes 6 transistors. Okay, so our number of SRAM cells is bigger than it was in the K-level mux, but less than it was in the 1-level mux. Our pass transistors, we have 16 in the first stage and only 4 in the second stage. So 16 plus 4, that's our pass transistors. And then we always have these 3 in this output structure. So if I put in the same things I had before, inputs are 16, and we make our pass transistors strong, so we make the drive of the pass transistors is equal to 5 times the minimum. I plug that into my area equation and my transistor count equation. I get the area is equal to 111 minimum width transistor areas. So it's actually smaller than the 1 level. It's also smaller than the K level. So this is usually the smallest. Usually it's 2 level. You can also try 3 level, but usually 2 level works the best. So it's the smallest. It's also faster than K level. So it's pretty small, or pretty fast. You only have 2 transistors in series discharging this node. And because the wires tend to be a bit shorter, this is usually not much slower than this. Usually it's a little bit slower, but not much. So it's a pretty good trade-off, and this is the dominant one that most commercial FPGAs use. Okay, hopefully you're with me. That might be more than you wanted to know about muxes, but this is a key thing, building block in FPGAs. I guess even with this though, so now we're building the muxes the most efficient way we know how to. The area of that's 111, the LUT was 217. We need 4 of these. 4 of them still bigger than LUT. Okay, so routing still really matters. Does that make sense? Yeah.
I'm curious about the number 5. So how is that 5 using calculation?
Basically, I have that calculation of my simple minimum width transistor area model was basically area of a transistor, including its spacing, was equal to 0.5 plus 0.5 times drive. Okay, so how is it used? It basically says this transistor will be 3 times the size of a minimum one. And I'm using that to get this number. Does that make sense? It doesn't change the calculation a whole heck of a lot, but I'm just trying to show you're trying to do a basic transistor sizing too. And you might go, well, how did you choose 5 times? The reality is you'd sit down and do some circuit design, maybe some spicing. It's a reasonable number, and I'm using it. So, yeah.
You said for the inverter and the weak pull-up thing.
Yeah.
That one we have a drive of 1, right?
Yeah.
That's why it's 3.
Yeah. I made these ones really small. And you could go, wait a sec, isn't this driving a routing wire? Shouldn't this be bigger? Probably, but I'm essentially thinking there'll be another inverter after this that's pretty big that's driving a routing wire. Does that make sense? Or if I need to drive something bigger, there'll be another inverter after that. And since it would be constant in all these calculations, I don't put it here. I have to sort of draw a box somewhere. Does that make sense? Okay, so yes, this is big. This is still not all our routing area. So this gets so we figured out the area of the LUT. We figured out the area to get signals from the routing wires into the LUT. We haven't figured out the area to get the LUT output connected to the routing wires or the routing wires connected to each other. So we actually still haven't worked out all of the routing area. That's what I'm going to do now. So we're going to try to work out how much. Essentially, I just did what's called the input connection box, like the muxes that connect me to the inputs of my block to the routing channels. Now I need to work out what about the switch block, which connects routing wires to each other. And with multiplexers, what I'm using here, it also connects the output of the block to the routing wires. Okay, so we're going to call it the general routing area. Okay, so this is a little harder to estimate. So if but I'm going to do a reasonable job. So if Isidore was concerned about my 16 to 1 mux, he may become concerned about some of my, the cavalier method in which I'm going to now come up with some other things. Okay, so routing area. Okay, so how do we estimate? Okay, so what I should really do is I should use a CAD flow because there's a lot of coupled decisions here. I should actually take a CAD flow, take a bunch of benchmark designs, place and route them with a certain mux size, certain channel width, see if it works well. And if it does, I take those as my values. And if it doesn't work well, I change the channel width or I change the mux sizes and I repeat. So I should do that. I'm not going to do that right now. Okay, so use CAD flow is the best. And we'll talk a little bit about that in some slides in another lecture or two. And you will do it in the last assignment. You'll run a CAD flow like that. But I'm not going to do that. What I'm going to do is I'm going to use a simple model to gain intuition. And this model is useful. It'll give us a reasonable estimate, not one where you'd want to publish a paper saying this is the only way I did it, but it's reasonable and it gives you more insight. Okay, so first thing I need is this equation. It's pretty simple. Okay, so WAV, the average channel width that I need, is equal to lambda times R bar over 2. Okay, so what are these things? Okay, so lambda is, so W average is basically the average number of wires I'm going to need per routing channel. That's my output. That's what I'm trying to figure out. Because I can't work out the routing area unless I know how wide I need to make my channels. Lambda is the average number of used inputs per block. Okay, so we're using a 4-input lookup table. That's our logic block. So what do you think lambda is? Average number of used inputs per block. Yeah, 4? Close. Okay, so 4 is an upper bound. It turns out that synthesis tools usually can't, even if you tell them what I've got on my chip is 4 LUTs, they can't always find a way to map everything to 4 LUTs. You'll wind up with some things that are 3 LUTs. Maybe there's like a register and then not much logic in another register. So it goes, look, it's just a 3 LUT or a 2 LUT. So there's a few reasons why it doesn't make everything 4 LUTs. But 4 would be a reasonable guess. I actually know that from tech mappers, we're going to use 3.5 in our case. All right, not too far off 4 though. Okay, so R bar. What is R bar? R bar is basically the distance. It's how well your place and route engine did. What is the average distance from the output of a block to the input where it has to go to? Okay? So it's the average distance from the output of a block to input. Okay, so if my LUT basically connects to the LUT right next to it, and that happened every single time, R bar would be 1. Okay, because you only go 1 unit over. That would mean your place and route engine was fantastic, and it would also imply your circuit's very local. If my, I look at a typical lookup table in my placement, and it actually has to go 2 units to the right and 3 units up, then R bar would be 5. Okay, and in practice it'll be a mix, right? Like some are going to go 7 units over, some are going to go 3, so it's the average number. And if my placement engine was really bad and everybody went halfway across the chip, maybe R bar would be like 150, because everybody's just going everywhere. Okay, so what's a reasonable value for R bar? This is really where a CAD tool is very helpful, but I've actually run a lot of CAD tools, and R bar, I'm going to assume, is about 4, which is a pretty reasonable value. Most circuits are pretty local. That's a pretty reasonable guess of how far the average connection has to go before it like reaches its destination. And let me draw you a little picture to make sure that this is, well, I guess they're divided by 2. is from 2 dimensions. Okay, so basically if half of our routing distance is horizontal and half is vertical, we should divide this by 2 to figure out well, essentially how much of our wiring was one dimension versus the other. So that's where the divided by 2 comes from. Let's see. What's that? Sometimes. We actually are using 3 dimensions sometimes. You have to ask Amin. So he loves being asked when the 3-dimensional support will be completely done. Yeah. In 3D, you would divide this by 3 if it was 3D and there was no preference to go in 2 dimensions versus the third. So.
If you were 3D, do you have control over the channel width in third dimension?
Within manufacturing ability. So I mean, you as an architect get to choose what it is, but if what you choose is not manufacturable, there will eventually be a reckoning. So.
The problem with power, like the heat dissipation.
That is another problem. As you stack dice, if they're high power, it's also a problem getting it out. So it's going to be hard to make it. I mean, you can have an FPGA array where it's 300 columns by 300 rows nowadays. It's going to make it hard to be 300 stacked dice because that's going to be hard to get power out of the middle. So it's true. You're probably never going to get a third dimension that's the same magnitude as the others. Maybe. I mean, Flash can do it. Flash can actually go very vertical. HBM, which is high bandwidth memory, it's DRAM, it'll go 8 high. We are in research looking at chips that are like 2 high for FPGAs. And yeah, DRAM can go 8 high. Flash is built a different ways. They build the transistors vertically, and modern Flash will often have, I forget the latest numbers, like 300 layers. Like they'll actually have 300 vertical transistors. But they don't do it with 300 dice. They do it by actually building layers of transistors on top of each other. So yeah, 3D is, depending on like exactly what you're talking about, it's kind of real everywhere. And for some, it's kind of like, it's 2.5D or 2.1D. But for some things like Flash, it's close to real 3D. So, okay, but that was a digression. Okay, so let me see. This is another one of those figures I always screw up. Let me try to show you what this means. And I'm going to do it in 1 dimension because 2 dimensions is too hard, but hopefully you can generalize. Okay, so what does r bar equals 4 mean? So let's see. Let's draw it. I'm going to draw it this way. Okay. I come out of here and I go 4 units over. Maybe I will put this one back. Okay. So that's what r bar equals 4 means. Go over 4 units. Okay. The typical connection. Let's say I repeat that over and over again. Then it means this block's output also would go over 4 units to some block here. This block's output would go over 4 units to some block here. This block's output would go over 4 units to some block here, and so on, okay? And I think I should have edited it here because it would make my diagram look neater. So I should define that as 4, like kind of start here, end there. And then this one would now be able to reuse this same spot because this wire is ended, okay? So this one would come out and would use this spot, this track, okay, to go over 4 units. In the steady state, if I draw a cut line across here, the number of wires I cut is 4. Does that make sense? So because everybody drove out one signal that went 4 over, once I repeat that 4 times, I wind up with 4 wires in parallel. And it doesn't matter how many times I repeat it because this ends, so the pattern just keeps repeating. It's always 4 wires. Hopefully it gets across the point of like, well, what does this R bar mean? If the average distance you go is 4 units, then you need 4 wires in parallel to make that work if you're trying to route a signal, okay, from every single block. But I'm actually not trying to route a single signal to every block. I'm actually trying to route 3.5 of them. Okay, so now I need to multiply that 4 wires by 3.5. So that's what this equation means. And it's actually an important one to understand. If you basically have a bad placement tool or your rent exponent is high, this R bar goes up, okay? You need a wider channel. If you build a bigger logic block and your lambda goes up, you need a bigger channel, okay? So the channels that so for a 4-input lookup table, I'm now trying to figure out what's a reasonable channel width. Okay, so if I plug in, well, I guess I'm not going to plug it in yet. I've got almost all the numbers I need. This equation is giving me the average number of wires that I have sort of crossing by any point in any channel. We're building, if you remember back to the routing architecture I was making, I'm using relatively small muxes to go in between the routing wires. I said I got a certain routing wire, and it could have an input from the left, an input from the right, an input from the bottom, if it was an upgoing routing wire, and an input from one LUT output. So it's kind of restricted. I don't have like a switch pattern where I say this routing wire can be driven by any wire that's near it. And the reason I didn't do that is because that turns into huge muxes that are actually going to cost me a lot of area. So I don't want to do that. I want to use small muxes. But what that means is I'm going to get some blocking in the routing pattern. First, there's going to be some hot spots where I just need more wires here because this part of the circuit has poor locality. And then because the switch pattern is more limited, I can't really use all my wires. If I tried to use every single wire, some of them are just going to be blocked. So I need to leave some sort of spare wiring so I can get around that. Okay, so what that means is we can't use all the wires in a channel. Okay, so I got that. W average is the average. And we need the peak. Okay, and I guess I told you the reasons why. Basically, we have a sparse switch pattern. Which is going to lead to blocked wires. We also will have some congestion hotspots. Congestion hotspots basically happen because circuits don't have the same rent exponent everywhere, right? There'll be like your finite state machines that are a little harder, and other parts might be a little bit easier. But for both those reasons, we don't want to build a chip where we made all the channels WAV because it's just not going to work. Like your CAD tools are just going to fail all the time, and you're going to get in a lot of trouble. So what you need to add, how much do you need to add? This is again where you'd run a CAD tool because it's difficult to say. But again, I've run a lot of CAD tools. A reasonable guess would you add about 50% to 100%. Extra W. So it's quite a bit. Why is it a broad range? I mean, it depends on lots of different things. Like I could make my muxes somewhat bigger, and then I'll be down more like the 50%. But from an optimization point of view, maybe that's a good idea because I made my channel wider in that saved area, but I also did make my muxes bigger in that cost area. So there's a trade-off there. If I chose to make my muxes relatively small, then I'm probably going to have 100% extra wire. And maybe that's a good idea or maybe not. Maybe because I made that results in more muxes, but each one is smaller. So maybe that's a better trade-off point, maybe it isn't. But this gives us a broad range, which is probably all we need right now. So we're going to we'll use 70%. We'll basically just take roughly the average of those two things. All right, and now we have kind of all the numbers we need to plug in. That's what I'm doing here. let's see. Okay, so if we take W equals lambda R bar over 2 times 1 plus this guard band that I just came up with. And I plug all those numbers in. 3.5 used inputs per block. R bar is 4 with a pretty good CAD tool. And I'm going to add a 70% guard band, or 0.7. I get W is equal to 12 wires per channel. Okay, so let's do a sanity test. So for a commercial FPGA like Agilex or Versal, do you know what the channel width is? For no reason you know the exact number, except maybe Amin. Amin might know. Any idea of roughly what it is? Yeah. No, so it's not 30. What do you think? Yeah, it's pretty high. It's probably like 300, maybe 400, right? Slowly going up as the chips get bigger because of Rent's rule, right? So much higher. So I just got 12, and if I go look at some of the leading commercial chips, I'm going to say maybe 300, maybe 400, right? Did we screw up? What do you think? Yeah.
A number of things. First off, they'll typically have, like because of their hierarchy in the routing, right, there's going to be multi-stages of muxing,
Mm-hmm.
so that allows you to have smaller channels, I think.
Well, that would, oh, you're saying how do I have smaller channels? Because you're saying
No.
my channel is much smaller than theirs.
Yeah.
So I need to figure out, like, did I do something wrong, or is there a reason why their channels are so much higher than mine?
Your logic block's a lot smaller.
Yeah, that's actually the key thing. So I'm using, on purpose, a very small logic block, a 4 lat. My lambda is 3.5. Let's take Agilex, because I know the architecture well. They have 10 more complicated lookup tables. Okay, so depending on how you count them, they have 10 or 20 lookup tables. So they have like 10 6-input lookup tables. So their number of inputs, they have local routing and so on, but they've got about 60 inputs. Okay, and I've got 3.5. So to first order, I would say, maybe I need to multiply. This equation says if everything else was the same, I need to multiply by around 20. So if I take this times 20, it's actually 360. It is actually in the ballpark then. So that's one of the reasons to have like equations like this. They give you intuition. This might seem like an insane answer, but it's very different because my logic block is very different. And yeah, if Agilex or Versal tried to use 12 wires per channel with the logic blocks they have, it would not be good. It would be a very challenging CAD problem. So what's that?
Each block's a lot more than 12 inputs.
Yeah, it would be bad, right? You wouldn't want. Oh, that's weird. Oh, I wonder if my Zoom meeting just died. What just happened there? Oh, my Zoom just died? Okay, well, hopefully the live stream still works. I'm not using a projector anyway. I think I should have plugged in. Okay, so we get 12 routes per channel, and while it seems crazy, it's not. Okay, so we're using a really simple routing architecture. Let me see if I can finish this off quickly. So we're using a simple routing arc. I showed it to you. It's basically length 1 wires and 4-to-1 muxes. That was what my whole routing architecture was. What does it look like? I've got a lookup table. Okay, so I'm not drawing 12 wires. I'm just going to draw 2 in each channel. Whoops. So I've got that. And I'm basically saying every single wire is driven on one end or the other. Okay, that's like a good routing architecture. It's like called direct drive or mux-based routing. And basically, I'm sending one signal in from kind of each of the terminating wires and one signal from the LUT. So I get a 4-to-1 mux. So what this allows me to do is allows me to connect the LUTs to the fabric, and no matter what direction I'm going, I can kind of keep going that direction or turn up or down. And that turns out to be enough to do a pretty reasonable job. Let's see. I got one board left. Okay, so let's take the area of this muxes. Okay, so it's a 4-to-1 mux. A 4-to-1 mux is so small, we're just going to do a 1-level mux. And we already calculated what that takes. We'll have 6 transistors for each SRAM, and there'll be 4 of those, plus 4 pass transistors. We're going to make them 5 times drive strength, so we're going to get this 0.5 plus 2.5 again, plus 3. Okay, so this is the SRAM. This is the 5 times drive pass trans. And this is the inverter plus the level restore. Okay, so we're just applying our mux equation. And these muxes come out to be smaller because there are only 4 input. So 39 of these minimum width transistor areas. I have a bunch of these muxes though. Okay, so area these are called the routing drivers. So I already got the area to get into the logic block. This is now the area of these switches between wires and to get out of the logic block. Well, I've got W of these wires in each channel. So I need W muxes. There's a horizontal channel and a vertical channel associated with every block. That's my repeated tile structure. So I need to multiply by 2, and then I need to multiply by that area that I just calculated. Okay, so I plug all that in. I said my channel's 12, 2 dimensions, 39 of these minimum width transistor areas, so I get 936 of these minimum width transistor areas, which is big. Okay, so it's even bigger than the input muxes. Okay, so now I have enough that I can actually get the area of the whole tile. Okay, tile meaning the LUT plus the routing that comes with it, and I could repeat this. Okay, so I got the area of the LUT plus 4. I need 4 of these inputs, and we already worked out what the input mux size was to get into the logic block. And then I need the area of these routing drivers, which I just calculated. Okay, and we have all these numbers. So it's 217 for the LUT, is 4 times 111 for the input port. It was 936 for the switches between the wires. So we get 1597 of these minimum width transistor areas. Okay, so what's interesting about this? The routing dominates. Okay, so if I work this out, it's 86% routing area. Okay, so what does this mean? You don't want to neglect routing area. There are actually some FPGA architecture studies where people, they're not good ones, but where people basically just try to work out, how many of the logic blocks do I use and how big is the logic block? And the routing's harder. You need CAD tools, you need to do more work, so they just kind of ignore it. You don't want to do that because the routing area is actually the dominant thing. You'd be better off, this is not a good idea either, but you'd be better off ignoring the logic and just paying attention to the routing. It's a big number, so optimizing the routing fabric is an important thing. You can do better than this. So I just did a pretty simple routing architecture. And if, with a bunch of techniques that we'll study in the next couple of lectures, or 3 maybe, you can make this better. But it's still, I've never seen an FPGA that was less than 50% routing area, and 70% is fairly typical. Okay, so you can probably take this as 86%. We can do better with optimization, but 50, 70%, those are pretty reasonable numbers. So don't neglect this. And that's it for today. So I went 4 minutes over. I'm close. So yeah.
Again, read the mux sizes. We have 12 wire channels, but we have 16:1 mux at the input.
I knew you were going to notice that. So but I have an answer. It's okay. Because there's nothing that says I have to just listen to one channel, right? So I have my input here, and I can say, okay, I'll listen to 8 wires from this channel and 8 wires from this channel. And that's actually a pretty good idea, because I'm listening to both the vertical and the horizontal, and it gives my router more options. So now you see the beauty of my 16. You're like, wait, so 12 wires, you chose 8 out of the 12 here, 8 out of the 12 there? It seems very reasonable, doesn't it? So. I'm actually, okay, so last year I just changed this example to use 16:1, because the first time I did this, I just arbitrarily picked 32:1. And then when I got to the end, I'm like, it's 32:1 and I only have 12 wide channels. It's kind of hard to defend. So I went through and redid it all with 16. And I'm glad I did, because if I had used 32 to 1 input muxes, then I think I would have had difficulty answering that question. So I love that question. It justified me redrawing these things. So, any other questions? Okay, thanks everybody. Bye-bye.